Good day to you, ladies and gentlemen, and welcome to the 11th lecture in the Jabrah Reinforcement Learning Series. So, today we're going to be continuing from where we left off in the previous lecture when we had started on Monte Carlo. But one thing to note is that up till now, we had been going through this dynamic programming methods for solving for reinforcement learning problems. And by that, I'm referring to policy iteration and value iteration. So under those methods, we had made a couple of assumptions, and one of major assumption was that we actually knew the model of the environment, and by that I mean that we knew how the environment changed or how the environment reacted based on how we acted on it, right? So we would know that if we're in a particular state and we take a certain action, with what probability we end up in different states. So we actually knew this whole probability distribution and stuff like that. That's the assumption that we made. But then in the last lecture, we asked ourselves the question: what if we're in a situation where we don't actually have this model of the environment, right? And this is kind of akin to situations that we would encounter in real scenarios when we're solving for this kind of problems. And this was the motivation behind introducing Monte Carlo. So in the last lecture, we introduced Monte Carlo with exploring starts. If you don't remember what that is, if you want to know what it is in detail, please look at lecture 10 of module 1, where we actually covered and where we talked about what this assumption actually is. And today we're going to be removing this assumption. And after removing this assumption, we're going to see what other techniques can we use to solve for this kind of problems using Monte Carlo. So as a light refresher, we had specified that, we had mentioned that Monte Carlo allows us to kind of create estimates of the Q values or the value function, right? It allows us to estimate it based on the episodes that we sample. So we basically sample a bunch of episodes and we average them and we gain these estimates, right? And we had distinguished between first visit and every visit Monte Carlo in the previous lecture. And the assumption of exploring starts being that we assume that every single time we generate a new episode, every state and action pair actually have a probability greater than 0 of being encountered every time we start a new episode. So in this lecture, we're actually going to remove this assumption of exploring starts. If you really need detailed information on what it is, please visit the previous lecture. We went through it, so I'm not going to go through it again in this video. So after actually removing this assumption, actually, before going there was something else I wanted to mention, which I should have mentioned in the previous video. So when we're dealing with reinforcement learning algorithms in general, there are two types of algorithms, and this is going to be quite important, especially now that we're starting in Monte Carlo. We're going to see both versions of these algorithms. So one of them is called let me use a different color for this. So we have on policy methods and off policy methods. So in the context of Monte Carlo, actually in general, so on policy methods attempt to evaluate or improve a policy that is actually used to make decisions. So the same policy that we are using to make decisions is the same policy that we're actually trying to, evaluate, and it's the same policy we're trying to improve. But in the case of off-policy methods, we attempt to evaluate and improve a policy different from the one that we're actually using to make decisions. So this distinction is going to be quite important because right now, for instance, when we looked at Monte Carlo with exploring starts, it was an on-policy method because we only had one policy and we're doing policy improvement and we're doing like policy evaluation and improvement and stuff like this on the same policy, right? we're not using a different policy to kind of like make those decisions. So since we're using the same policy for doing this evaluation and improvement, this is kind of like an on policy method, right? So far we've only seen on policy methods. We have not encountered any off policy methods, and we will do that in a future video. So I just wanted to introduce this distinction because in the future we'll be using these terms. So it's important. It might be important for you to know what this actually means, right? So anytime someone mentions, "Oh, this is an off policy or non policy method," you know that this is what they're talking about. Having said that, so in on policy like control methods, right? The policy is generally soft, right? So what do we mean when we call a policy soft? So there's a certain group of policies, right, that we're gonna go through today that are called epsilon-soft policies, right? This is the kind of policies we're going through today. They're called epsilon-soft policies. So what are epsilon-soft policies? Well, it means that essentially, uh, let me kind of change the color here. So when we're talking about epsilon-soft policy, we're saying that the probability of taking an action, given that you're in a particular state, should be greater than 0, right? For all states, right? For all S is an element of S, and all actions. All A is an element of AS. So for all states and all actions, the probability of actually taking an action in a particular state should be greater than 0. This is what it is, an epsilon-soft policy. But then we're going to say this is shifted closer to a deterministic optimal policy. So what exactly that means? That in the beginning, right? So this is kind of like an important concept in reinforcement learning that is known as exploration versus exploitation, right? And this is kind of like if you've got a policy whereby you say that if I'm in a particular state, right, and I want to take a bunch of actions in the state. So if every single action has a probability greater than 0 of being taken, then we've got something that has a bit of exploration in it, right? So because every action actually has a chance of being taken, and we are going to need this, right? Because if you remember, if you think about it, in Monte Carlo we're sampling episodes. So if we don't actually kind of make this kind of assumption of epsilon soft policies, we're gonna miss certain states, certain actions, sorry. We're not gonna take certain actions sometimes. So in order to make sure that we actually find the true optimal policy, we need to make sure that all actions are explored in some way, which is why these epsilon soft policies exist. That's kind of like the motivation behind this. But this is just a definition. We're going to go into all the details, of course. I'm just trying to define what epsilon soft policy is. So this is kind of what the definition becomes, right? But, and the thing is that under the group of epsilon soft policy, there is a certain type of policies that are called epsilon greedy policies, right? So under this, right, under this, we have a certain group of policies called epsilon greedy policies. And these are generally what we're going to be going through, more or less, like the epsilon greedy policies. And this means actually that most of the time we're going to be take the greedy action, right? So what are epsilon greedy policies? We're just saying most of the time we are taking the greedy action. So you might ask yourself at this point, what is a greedy action? Well, you should actually kind of have an idea of what it is, uh, given that you're given a q value s comma a, right? And you take an argmax over all actions, right? For this value, I should have used a different color for this, I'm sorry. But if you take an argmax over this is a greedy action, right? This is a greedy action because it's the optimal action in this case. So since from the beginning we are kind of like starting from a suboptimal policy, um, always taking a greedy action is not going to allow us to explore other possible actions that might turn out to be better. Because we're basing these actions on a suboptimal policy, we evaluate a suboptimal policy and we start taking actions based on this. And so it becomes quite important when actually sampling, to explore other possible actions that you could be taking. That's essentially what's happening here. So right now, it's just a bunch of definitions. We haven't actually gone into the core material here. Mm, but now we need to properly define what we're doing at this point, like properly define what an epsilon soft or an epsilon greedy policy is in our context. So I'll shift to a new page to do that. So let's start. First of all, we need to take greedy actions with a certain probability and non-greedy actions with another probability. So we're going to say that we're going to take non-greedy actions with a probability that's equal to epsilon, right? This is kind of like, yeah, epsilon is going to be the probability that we are taking our non-greedy action, but we're gonna say epsilon over the number of actions, right? So this AS is just means cardinality. So what does this mean? So let me give you an example, a short example. So let's say we can take, we're in a particular state here. Our state is state S, and we can take action 1 or action 2 or action 3, right? Or we can take action 4. So by actually stating it like this, we can now say what is the probability of taking action 1, action 2, action 3, and action 4, right? So this is what we are considering as this. So what is the cardinality of AS, right? Actually, first let us define AS. Here AS is a set of all these actions A1, A2, A3, and A4. So it's a set. So a cardinality of a set in this case, we're just counting how many elements we have in that set, right? So when we actually take this, in this case, this is equal to 4, right? So we are given an epsilon probability to all of our actions, and the remainder of the probability is going to go to our greedy action. So what does that mean? So that means that greedy action probability is equals to 1 minus epsilon plus, right, epsilon over this set. So why are we saying this again? So if you can think of it this way, let's if we define epsilon to be kind of like the probability of each and every one of this action being taken, right? So 1 minus epsilon should be the remainder. So in this case, since we have action 1, action 2, action 3, and action 4, we know that each and every one of them has at least this much probability of being taken, right? But the greedy action also has an additional 1 minus e so that our probabilities sum up to 1. This is just to ensure this, right? That our probabilities are ultimately like sum up to 1. So so basically that's what's important here, like to note that epsilon plus 1 minus epsilon, this should sum up to 1. So non-greedy action probability and greedy action probability. Of course, this also includes the greedy action here, which is what's removed over there. So please note it like that. So having said that, one of the thing is that in the group of epsilon-soft policies, epsilon greedy policies are actually kind of the closest to being like greedy in this kind of set. So having said that, let's actually now go through the pseudocode, right, for this algorithm. So I will set a new page. And what is the code that we're gonna go through? We're gonna call it on policy. First visit Monte Carlo control for epsilon soft. So this is for epsilon soft policies, right? This is the algorithm we're going through, right? So what are we gonna start with? We're gonna start with a small epsilon that is greater than 0. So again, if you remember what this was, when we're talking about epsilon, this is just the probability of kind of taking a uh, a non-greedy action, right? In this case. So this is what this epsilon is. We're gonna divide it across all of our actions, and after doing that, we're actually it would have been, of course, easier to just say epsilon divided by the non-greedy actions, but there's actually a reason for this representation of attributing this value to all 4 actions and then just adding it back here. We're gonna go through that, but please try to convince yourself why this works in this way. So we're gonna start with a small epsilon, and we will initialize the following. Initialize. So we're gonna start by initialize pi. What is pi? Pi is an arbitrary epsilon soft. This is the keyword. Epsilon soft policy. That's what pi is. So pi has to be an epsilon soft policy in this case. And what that means is that the probability of taking an action in any state should always be greater than 0, right? And then q s comma a. So we just assign this, right? Again, arbitrarily to some values, like we can initialize it to 0 or whatever. For all s is an element of s, and for all a is an element of as. So this is how we initialize our q values, and then our return. So this kind of initialization should be quite familiar, maybe except for the whole epsilon soft policies, if you followed in the previous video. So this is just an empty list, right? So that's how we start our initialization. And then we're going to repeat the following. We're going to repeat the following. So generate an episode using pi, right? So we're going to use pi, the current policy, to generate an episode. So this should give us like S0, comma A0, comma R1, comma S1, all the way until we reach some value RT, right? So this is kind of from lecture 1 anyway, like how do we, lecture 1 or 2, like how do we actually generate episodes and stuff like that. So this is what we're going to do, generate an episode using pi, and after that we're going to set g, the return, to be equal to 0, right? And then loop for each episode. So for each episode we're generating, and here's the key thing here, we're looping in reverse. So we're going from t minus 1 to t minus 2, t minus 3. So t is the final time step. Since we have the whole episode, we can of course loop from forward to back or back to forward, but this way is actually more efficient. And again, as an exercise, try to convince yourself why that is. Like, what's the advantage of looping backwards as opposed to looping forward? And think of it from a memory perspective. This is more of an algorithm type of question, but you don't have to concern yourself with it for now. So we're looping for each episode going in reverse, right? So what are we doing? We're attributing that g, right, the return, is equal to RT plus 1, right, plus gamma times g, right? So what is the value of g, right? For each episode, we're just updating it by the same equation that we've been using throughout, like the reward you get plus gamma times the g that you already had in the previous step. So this is kind of like how we update this value. And then if, right, st comma at does not, this is a keyword, does not appear in S0, comma A0, all the way up to ST, comma ST minus 1, right? So if STAT does not appear in here, it means it only appears once, right? So this is a first visit. If we look back up here, we're doing first visit Monte Carlo. So since we're doing first visit Monte Carlo, we want to find the first instance that we encountered the state. So since we're looping in reverse, we're just saying that if we start at some later time step, we should not find the state action pair in the previous time steps, because if it appears in the previous time step, then we're not dealing with its first visit yet. So this is kind of why that is. So if st, at does not appear in this, what are we going to do? Well, we're going to append g to return, or st, at, right? That's where we append g to this returns. Then the q value, right, of st, at, well, This is just the average. This is just the average of the returns of st, comma at. That's how we compute the q value, because the average, same as the algorithm that we went through last time with exploring stars, right? And then what's the optimal action to take? So the optimal action, as you know, this should be the argmax over all actions of q st, comma a, right? So this is kind of like the argmax over all actions. That's what the optimal a star is, right? But now, are we going to act according to the optimal action? No, we're not. How do we act? So what we do is kind of like how we update our policy, essentially, um, for all, right? So this is control. So we care about updating the policy. For all actions that are an element of AST, right? For all actions in our action space. What are we going to do here? Well, we update our policies pi of A given ST. How do we act here? Well, this is simple. We already know what this is. We covered it in the previous slide. This is 1 minus epsilon plus epsilon over the cardinality of AST if A equal to A star, right? Or it's epsilon over the cardinality of AST if A is not equal to A star, right? So we updated our policy, but we updated it by using this probability distribution over the action space. So our policy becomes that um, if it's actually the kind of the if in that state, if it's the optimal policy, like how do you act with a certain probability of 1 minus epsilon plus epsilon over the cardinality of a st, this probability, sorry, so with this probability we act optimally, right? And with the remainder of this probability we act suboptimally. And this is to enable, let me use a different color to do this. This is to enable exploration, right? To explore other states. And this is exploitation, right? Why? Why do we say it's exploitation? Because ultimately we want to act according to the optimal policy, and the optimal policy is given by A star, which is the argmax over all actions. We cannot always be exploring, which is why epsilon continues to decrease the further we go. So that should explain what this is. So we've gone through the basic pseudocode of how we what you call it, how we can do Monte Carlo after removing the assumption of exploring stars, and we're doing it for control as well in this case, as you can see. So I hope that this actually was clear enough for you to understand how this algorithm is going. Please note that in this case, you can actually just rewrite this. For instance, this section here, you don't have to loop in reverse, of course. Of course, you can actually loop by saying t is equals to 0, comma 1, comma 2, comma up to t. But what would change, right, in this case is that you now need to maintain, because you now need to check that, okay, this is the first time that I encounter a state in this time step, right? But now you need to maintain a whole list of states that you actually visited, right, in this case, so that you can update them later, which is essentially what's happening here. But it's up to you, of course, like how you wanna traverse through. This is just the way that it was written in the at least the second edition of the book that I'm going through, and try to convince yourself. Try to even write it. Try to even write it the pseudocode by looping in the other direction and see how it would change. This would be a good exercise to actually understand what's going on. So with that said, this should kind of like give you a clear understanding of what's happening here. And finally, there is an assertion that for any epsilon-soft policy pi, any epsilon greedy policy with respect to q pi is guaranteed to be better than or equal to pi, right? So this is kind of like an assertion that's made, and you can prove it by using the policy improvement theorem itself. Essentially, it's the same thing that we were doing when we were covering what do you call this? The policy improvement in the policy iteration algorithm, right? So we're actually going through a similar proof for doing this. So um, for this lecture, since it's kind of repetitive doing that, I'm just going to skip through that. But if you want, please go through Richard Satton's book on reinforcement learning into that proof, and you can look at it yourself. Thank you kindly. The lecture, I'll finish it here.